Look up at the night sky. What do you see? Pinpricks of light, distant suns, islands of stars separated by unimaginable gulfs of emptiness. For centuries, that has been our view of the cosmos, a vast, cold, and lonely expanse. But what if that perception is one of the greatest illusions of all? What if, hidden beneath the veil of darkness, every galaxy, every star, every particle is intimately, instantaneously connected? What if the universe is whispering secrets to itself across billions of light years, bound by an invisible thread so strange that even Einstein called it spooky action at a distance? This isn't science fiction. This is the frontier of a new reality, a paradigm shift so profound it threatens to rewrite the textbooks of physics. We are beginning to uncover evidence that the bizarre rules of the quantum world, a realm where particles can be linked in such a way that affecting one instantly affects its partner, no matter the distance, might not be confined to the infinitesimally small. This phenomenon, known as quantum entanglement, could be operating on the most colossal stage imaginable, the scale of entire galaxies. Imagine two swirling galaxies, separated by half the universe, dancing to a tune neither can hear but both perfectly know. This is the breathtaking possibility of entangled galaxies, and if this is true, the implications are staggering. It means the cosmos is not a collection of isolated objects but a single, interconnected web, a cosmic neural network where information flows in ways we are only beginning to fathom. This discovery doesn't just belong in the realm of theoretical physics. It has the potential to ripple out and touch everything. It could unlock technologies that sound like magic today, instantaneous communication across interstellar space, engines that harness the fabric of spacetime itself, and a complete redefinition of what we consider reality. This journey we're about to take together will explore how this cosmic connection could reshape our future, transforming our daily lives and our very place in the universe. So let's dive into the deep end and explore how the spooky link between atoms might just be the force that binds the cosmos. To grasp this cosmic idea, we first need to understand the quantum rulebook. Think of it like this: in our everyday world, if you have a pair of dice, what happens to one die has absolutely no effect on the other. You could roll one here on Earth and the other on Mars, and their results would be completely independent. But in the quantum realm, the rules are flipped on their head. Imagine a special pair of quantum dice. The moment you create them, they become linked in a mysterious partnership. You don't even need to look at them to know they're connected. Now, you send one of these dice on a journey to a distant star system. Back on Earth, you finally roll your die. It shows a 3. At that exact instant, without any signal traveling through space, the die light years away knows its partner has been rolled and instantly shows a 3 as well. This bizarre connection is the heart of quantum entanglement. It's a property where two or more particles are generated or interact in such a way that the quantum state of each particle cannot be described independently of the others. They become a single, unified system. This idea was so unsettling to the giants of physics that it sparked one of the greatest debates in scientific history. Back in 1935, Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper highlighting what they saw as a profound problem with the then new theory of quantum mechanics. They argued that if quantum mechanics was correct, it would lead to this spooky action at a distance, which violated the central principle of his theory of relativity, that nothing can travel faster than light. Einstein believed this spookiness was proof that quantum theory was incomplete, that there must be some hidden variables we hadn't yet discovered that would restore a sensible, local reality where influences need time to travel. For decades, this remained a philosophical puzzle. Then, in the 1960s, physicist John Bell proposed a way to test it. Bell's theorem provided a mathematical framework to distinguish between a universe with hidden variables and one with true spooky action. The experiments began, and by the 1980s, the results were clear and revolutionary. Teams led by scientists like Elaine Aspect conducted incredibly precise tests measuring the properties of entangled particles. Time and again, the results confirmed Einstein's worst fear: the spooky action was real. When you measure a property of one entangled particle, like its spin or polarization, its partner, even if it's miles away, responds instantaneously. This connection doesn't rely on any known force or signal. It seems to be a fundamental feature of our universe, woven into the very fabric of reality. It defies our classical intuition about cause and effect, suggesting that at the deepest level, separation itself might be an illusion. But if this spooky connection is so fragile that it seems to vanish for anything larger than a single atom, how could it possibly operate on the scale of something as vast as a galaxy? This is the monumental leap we need to make, moving from the quantum realm to the cosmic stage. The primary obstacle to this scaling up is a process known as decoherence. Think of a quantum state as an incredibly delicate and precise musical note, like a single, pure tone from a tuning fork. In our warm, noisy, everyday world, that note is instantly drowned out by the cacophony of the environment. The jostling of air molecules, the hum of background radiation, the sheer chaos of trillions of interactions. This environmental interference forces the quantum system to pick a state, collapsing its fuzzy, multiple possibility nature into the single, definite reality we observe. This is why we don't see quantum superpositions in our daily lives. A cat cannot be both alive and dead because the environment acts as a constant observer, forcing a collapse almost instantly. However, the emptiness of space presents a completely different set of conditions. Far away from stars and planets, in the deep void between galaxies, the environment is profoundly cold, dark, and sparse. The temperature is just a few degrees above absolute zero, and the density of matter is almost zero. In these near-perfect vacuums, the primary causes of decoherence are dramatically reduced. There are very few atoms to bump into a quantum system and very little thermal radiation to disturb it. This isolation could, in theory, allow quantum effects to persist for much longer durations and over much larger distances than we ever thought possible on Earth. It's the difference between trying to hear that pure tuning fork note in the middle of a roaring rock concert versus in the absolute silence of a soundproof chamber. This opens the door to a truly radical idea: that the largest structures in the universe might be the very places where quantum weirdness can flourish. Some theoretical physicists are now exploring models where the gravitational field itself, the force that sculpts galaxies and clusters, could be a medium for quantum entanglement. Gravity is exceptionally weak compared to other forces, but it has an infinite range and cannot be shielded. If two particles are entangled through their gravitational interaction, this connection might be preserved across cosmic distances because there's so little in the void of space to disrupt it. Pushing this idea even further, researchers are investigating whether the entire universe, in its earliest moments after the Big Bang, was a single, intensely hot and dense quantum system. As the universe expanded and cooled, these primordial quantum connections between particles might not have simply vanished. Instead, they could have been stretched and frozen into the large-scale structure we see today, meaning that galaxies which appear separate to us are, in fact, parts of an ancient, entangled web. The cosmic microwave background radiation, the faint afterglow of the Big Bang, is now being scrutinized for subtle statistical patterns that could be the fossilized imprint of this primordial quantum entanglement, a whisper from the dawn of time hinting at a connected cosmos. So if the void of space offers a pristine sanctuary for quantum weirdness, where might we actually see its effects? We look up not at individual stars, but at the grandest map of all, the universe in its entirety. For decades, astronomers have been meticulously charting the positions of millions of galaxies, and a breathtaking pattern has emerged. It's not a random scattering of islands in a dark ocean. Instead, galaxies are arranged in a vast, intricate architecture that resembles a cosmic spiderweb. This is the large-scale structure of the universe, an immense network where galaxies cluster into dense knots, strung together by long, faint threads known as filaments, all separated by enormous, empty regions called voids. This is the cosmic web. Picture the universe not as a collection of separate objects, but as a single, breathing entity. The galaxies are like glowing dewdrops clinging to the strands of an invisible web. And what is that web made of? The current understanding points to dark matter, a mysterious, invisible substance that makes up about 85% of all the matter in the cosmos. Dark matter's gravity acts as the skeleton upon which the visible universe is built. It forms the filaments that guide galaxies into their web-like pattern over billions of years. But here's where our hypothesis takes a leap. What if these dark matter filaments are more than just gravitational scaffolding? What if they are also the cosmic equivalent of fiber optic cables, conduits for quantum entanglement on a scale we can barely comprehend? This idea suggests that the quantum connections born in the universe's first moments didn't just fade away. As the cosmos expanded, these primordial entanglements were stretched across space, imprinted onto the distribution of matter. The filaments of the cosmic web, forged by gravity, could have preserved and even amplified these spooky links. In this view, two galaxies lying on opposite ends of the same filament aren't just distant relatives. They could be quantum twins, their fates intertwined since the beginning of time. Their connection wouldn't rely on a signal traveling at the speed of light along the filament. Instead, it would be instantaneous, a fundamental property of their shared existence within the web. How could we possibly test such a far-out idea? The clues might be hidden in the faint light of the cosmic microwave background, that ancient afterglow of the Big Bang. Scientists are searching for peculiar correlations in this radiation, patterns of hot and cold spots that are too perfectly synchronized across vast distances to be explained by conventional physics. These anomalies could be the statistical fingerprint of primordial entanglement, a ghostly signature left behind when the cosmic web was first being woven. Furthermore, by studying the precise motions of galaxies within the web, astronomers might find evidence that their movements are subtly correlated in ways that gravity alone cannot account for, as if they are all responding to an invisible, interconnected rhythm. This transforms our understanding of the universe from a mere collection of objects into a single, unified system, a cosmic neural network. Each galaxy could be thought of as a node in this network, with the filaments acting as the connections through which information or perhaps influence flows. The universe begins to look less like a machine and more like a living, thinking structure, with entanglement as the fundamental process that binds it all together. This isn't just a new chapter in astronomy, it's a complete rewriting of the cosmic story, suggesting that connection, not separation, is the true nature of reality. So where do we search for the ghostly fingerprints of this cosmic connection? The answer lies in the oldest light we can see, a faint whisper of radiation that fills every corner of the universe. This is the cosmic microwave background, and it's our most powerful time machine. Picture the universe not in its vibrant modern form, but as a seething, opaque soup of plasma, so hot and dense that light was trapped, constantly bouncing off a fog of particles. This was the universe when it was only about 380,000 years old. Then, in a pivotal moment, it expanded and cooled just enough for atoms to form, clearing the fog and allowing light to travel freely for the first time. That first flash of light has been stretching and cooling ever since, and today we detect it as a uniform microwave glow, a snapshot of the infant cosmos. Within this seemingly uniform afterglow, however, are tiny, telltale variations, ripples of slightly warmer and cooler spots. These fluctuations are the seeds of all future structure, the gravitational blueprints for galaxies and clusters. For the most part, these patterns align with our standard model of cosmic evolution, driven by gravitational instabilities, but there are anomalies, strange features that stick out like a wrong note in a symphony. Some of these cooler and warmer regions on opposite sides of the sky appear to be correlated in a way that defies conventional explanation. According to the rules of classical physics, these regions should have never been in contact with each other. There hasn't been enough time since the Big Bang for light or any influence to travel between them, even at the speed of light. It's as if two musicians on opposite sides of a vast concert hall began playing a perfectly synchronized duet without any signal or cue. This is where the idea of primordial entanglement offers a breathtaking explanation. If these distant parts of the universe were quantum entangled before the period of rapid expansion known as inflation, their connection would be a fundamental property of their existence, not something that needed to travel through space. Inflation would then have stretched these infinitesimally small quantum links to astronomical sizes, imprinting the spooky correlations directly onto the fabric of spacetime. When the cosmic microwave background was released, it carried this signature, freezing the evidence of a connected cosmos into the sky for us to find billions of years later. Scientists look for this signature in the specific statistical properties of the temperature fluctuations. They search for correlations that are stronger than what standard physics predicts, particularly between points in the sky that are causally disconnected. It's a bit like finding two identical, complex snowflakes falling miles apart. The chance of that happening by random chance is so infinitesimally small that you have to conclude they were formed from the same unique conditions. Similarly, the precise patterns of harmony in the cosmic microwave background could be the statistical snowflake that points back to a universe that was born as a single, entangled quantum state. Beyond temperature, an even more subtle clue may lie in the polarization of this ancient light. Polarization is the direction in which light waves vibrate, and the pattern of polarization in the cosmic microwave background, often called B modes, is like a fossilized record of the universe's very first tremors. These tremors, gravitational waves from the inflationary epoch, could themselves carry the imprint of quantum gravitational fields that were entangled. Finding a specific, anomalous pattern in this polarization would be like discovering the original signature on the cosmic birth certificate, a direct signal that the universe's largest structures are bound by quantum threads. While the search is incredibly challenging, with experiments like the Simons Observatory and the Lightbird satellite mission pushing the boundaries of detection, the potential reward is monumental. Solid evidence that the universe is not just a collection of parts, but a profoundly interconnected whole. Now, let's turn our attention to one of the most perplexing puzzles in modern cosmology, a mystery that has baffled astronomers for decades: dark matter. We know it's there because of its profound gravitational influence, yet it remains completely invisible, refusing to interact with light in any way we can detect. But what if its elusive nature is not just a matter of what it is, but how it's connected? This leads us to a fascinating and radical proposal. Could dark matter particles themselves be inherently entangled with one another? Think of the vast halos of dark matter that are believed to surround every galaxy. These halos are the gravitational glue that holds galaxies together, providing the extra pull that keeps stars from flying off into space as the galaxy spins. The standard model treats these halos as a sort of diffuse cloud of individual particles, each moving under the influence of gravity alone. But if those particles are quantum entangled, the entire system changes. Instead of a cloud of independent actors, the dark matter halo becomes a single, coordinated quantum network. The particles within it aren't just responding to local gravity, they are instantaneously aware of the state of their entangled partners throughout the entire structure. This could introduce a new kind of quantum cohesion that governs how the halo forms and maintains its shape. this idea might offer a compelling solution to one of the key pieces of evidence for dark matter: galactic rotation curves. When astronomers measure the speed at which stars orbit the center of a galaxy, they find something astonishing. According to Newtonian gravity, stars on the outer edges of a galaxy, where visible matter is sparse, should orbit much more slowly than those near the center. But that's not what we observe. Instead, the rotational speed remains nearly constant from the core to the far outskirts, as if there's a huge amount of unseen matter, dark matter, providing extra gravitational pull. But the exact distribution of this dark matter needed to create these flat rotation curves has always been a fine-tuning problem for cosmologists. An entangled dark matter halo could naturally produce this precise gravitational effect. If the particles are connected, their collective behavior would be far more organized and unified than a simple cloud. This quantum link could create a specific, stable density profile within the halo, one that perfectly explains the observed rotation of galaxies without requiring any ad hoc adjustments. The entanglement would ensure that the halo responds as a coordinated whole to the gravitational dynamics of the galaxy, maintaining a balance that keeps orbital velocities constant. In essence, the spooky action at a distance wouldn't just be a curious quantum effect. It would be the invisible hand sculpting the very architecture of galaxies. Furthermore, this perspective could shed light on other dark matter mysteries, such as the cusp core problem. Simulations of cold dark matter often predict that halos should have a sharp density peak or cusp at their center. However, observations of many dwarf galaxies suggest their dark matter cores are actually much smoother and flatter. If dark matter particles are entangled, their quantum properties could prevent them from collapsing into such a dense cusp. The same non-local connections that provide cohesion might also create a kind of quantum pressure, effectively fluffing up the core of the halo and resolving the discrepancy between simulation and observation. This isn't just adding a new particle to the equation. It's adding a new relationship between particles, a relationship that could fundamentally alter our understanding of the cosmos's hidden scaffolding. But if entangled dark matter shapes the hidden mass of the cosmos, then an even deeper mystery awaits, the force that is tearing the universe itself apart. We call this force dark energy, and it represents the single most dominant component of our universe, making up about 68% of all its energy. For the last several billion years, dark energy has been causing the expansion of the universe to accelerate, pushing galaxies away from each other at an ever-increasing rate. It's as if a strange, repulsive gravity is woven into the fabric of empty space itself. But what could possibly be the source of such a pervasive and powerful effect? The answer might lie not in the particles we see or even the dark matter we don't, but in the nature of nothingness itself, the quantum vacuum. To understand this, we need to redefine what we mean by empty space. In our everyday experience, a vacuum is just nothing, a complete absence of matter. But in quantum physics, the vacuum is a seething, bubbling cauldron of activity. Due to the Heisenberg uncertainty principle, empty space is never truly empty. Instead, it's a dynamic sea of virtual particles that constantly pop into and out of existence in fleeting particle-antiparticle pairs. They borrow energy from the vacuum for an incredibly brief moment, annihilate each other, and return the energy, all happening far too quickly for us to directly observe. This frantic activity isn't just theoretical. It has real, measurable consequences, like the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a slight push because the quantum fluctuations between them are restricted. Now, here's where it gets truly fascinating. Each of these virtual particle pairs is, by its very nature, born entangled. They are a single quantum system created together. Normally, their influence is localized and their energy contributions cancel out almost instantly. But what if, on the grandest of scales, this constant creation and annihilation of entangled pairs isn't perfectly balanced? The collective energy of this quantum vacuum could exert a tiny, persistent pressure. In fact, when physicists try to calculate the energy density of this vacuum, they run into a famous problem. Their theoretical predictions are astronomically larger than what we observe from dark energy. This is known as the cosmological constant problem, and it's one of the biggest unsolved puzzles in physics. The numbers are off by a factor of 10 to the power of 120. That's a 1 with 120 zeros after it. It's the worst prediction in the history of science. This is where the concept of large-scale entanglement offers a potential pathway to a solution. The key idea is that entanglement might act as a cosmic regulator for this vacuum energy. In the chaotic frenzy of the quantum vacuum, most virtual particle interactions are random and uncoordinated. But if entanglement links vast regions of space, perhaps along the filaments of the cosmic web we discussed earlier, it could impose a degree of order on this chaos. Instead of trillions upon trillions of independent, random fluctuations, the vacuum's activity could become correlated over cosmic distances. This large-scale coordination could lead to a situation where the repulsive effects of these entangled virtual particles don't perfectly cancel out. Instead, they could generate a small, steady, and collective push that permeates the entire universe. This net repulsive force would be incredibly weak locally, which is why we don't feel it on Earth, but when summed across the immense volume of the cosmos, it becomes the dominant force driving the accelerated expansion we attribute to dark energy. In this breathtaking view, dark energy isn't caused by some exotic new field or particle. It emerges naturally from the quantum vacuum, but its strength is set by the architecture of entanglement woven into the universe's fabric. The same spooky connections that might bind galaxies through their dark matter halos could also be governing the energy of empty space, linking the fate of galaxies to the deepest quantum nature of reality. The expansion of the universe, then, is not a runaway train driven by an unknown force, but a direct reflection of the quantum connectedness of the cosmos. The galaxies racing away from each other are dancing to a rhythm set by the entangled whispers of the vacuum itself, a rhythm that began in the first moments of the Big Bang and will continue to dictate the ultimate destiny of everything we see. But if dark energy whispers of a connected vacuum, there are places in the cosmos where quantum connection is shouted from the rooftops by gravity itself. We now venture to the most extreme environments imaginable, black holes. These cosmic monsters are often seen as the ultimate endpoints of reality, places where the laws of physics break down. Yet, they might also be the universe's most powerful engines of entanglement, and the key to understanding a paradox that has haunted physicists for half a century. This is the black hole information paradox, and it strikes at the very heart of what we know about quantum mechanics. The problem begins with what happens when something falls into a black hole. According to Einstein's general relativity, a black hole's event horizon is a point of no return. Once matter or light crosses this boundary, it is lost forever to the outside universe, its identity seemingly crushed into the black hole's singularity. The only properties a black hole has, according to this view, are its mass, its electric charge, and its spin. This idea is sometimes called the no-hair theorem, suggesting black holes are remarkably simple objects, void of any intricate details about what fell in. But here's the conflict. Quantum mechanics has a fundamental rule called unitarity. It states that information, the specific identity and quantum state of every particle, can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must be preserved. So, what happens to the information about a star that collapses into a black hole, or an astronaut who makes the fatal plunge? If the black hole eventually evaporates over eons through Hawking radiation, as Stephen Hawking theorized, does that information leak back out, or is it lost forever, violating a cornerstone of quantum theory? This paradox set the stage for one of the most profound and elegant ideas in modern theoretical physics, the ER=EPR conjecture. This might sound like cryptic jargon, but it represents a brilliant synthesis. ER stands for Einstein-Rosen bridges, which is the technical name for wormholes, theoretical tunnels in spacetime that could, in principle, connect two distant points. EPR stands for Einstein, Podolsky, and Rosen, the very trio who first identified the spooky problem of entanglement back in 1935. For decades, these two concepts, wormholes and entanglement, were thought to be completely unrelated. One was a dramatic feature of the large-scale geometry of spacetime. The other was a weird quantum connection between particles. The groundbreaking proposal, largely championed by physicists like Juan Maldacena and Leonard Susskind, is that they are, in fact, two sides of the same coin. The conjecture suggests that what we perceive as quantum entanglement between two particles might be physically manifested as a microscopic wormhole connecting them. Think of it this way: if two particles are entangled, they aren't just magically linked. They are literally tied together by an unimaginably tiny tunnel through the fabric of spacetime. This wormhole is not a tunnel you could travel through. It's a purely geometric connection that enforces the correlation between the particles. This idea provides a potential solution to the information paradox. When something falls into a black hole, its information isn't lost behind the horizon. Instead, it might be transferred through a wormhole, an ER bridge, to another part of the universe, or perhaps even to another black hole that is entangled with it. The information is preserved, not destroyed, maintaining the sacred rule of quantum mechanics. Now, let's scale this idea up to a truly cosmic level. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, an entity weighing millions or even billions of times more than our Sun. These colossal objects are not isolated, they are the anchors of their galactic domains. If the ER=EPR conjecture holds true, then the immense gravitational fields of these supermassive black holes could be factories for entanglement on an astronomical scale. The process of matter spiraling into the black hole's accretion disk, heated to incredible temperatures, could generate vast numbers of entangled particle pairs. Due to the extreme gravity, these pairs might be ripped apart, with one particle falling past the event horizon and the other escaping into space as Hawking-like radiation. But here's the crucial twist. According to the conjecture, the escaping particle and its infalling partner would remain connected by a microscopic wormhole. This isn't just a link between two particles, it's a stitch in the fabric of spacetime itself. Now, imagine this process happening not just once, but continuously over billions of years at the core of a galaxy. Each escaping entangled particle carries with it a thread, a wormhole connection back to the black hole. If these particles then travel across the galaxy, or even interact with the halo of entangled dark matter we discussed earlier, they could weave a complex web of spacetime tunnels. The supermassive black hole would act as a central hub in a vast quantum network. This leads to an even more staggering possibility. What if the supermassive black holes at the centers of two different galaxies are themselves entangled? They could have formed from the same primordial density fluctuation in the early universe, or perhaps even be connected by the cosmic web's filaments. If two such black holes are an EPR pair, then the ER=EPR conjecture suggests they are connected by a macroscopic wormhole, a true navigable bridge through spacetime. While this wormhole might be unstable or impractical for travel, its existence would mean that the two galaxies, separated by millions of light years, are fundamentally united. They would be quantum twins, their fates intertwined through a connection that bypasses the space between them entirely. The central black hole becomes more than a gravitational anchor. It becomes the heart of a galactic-scale entangled system, potentially allowing for a form of instantaneous correlation between the evolution of stars, the distribution of dark matter, and even the mysterious effects of dark energy across unimaginable distances. In this view, black holes are not destroyers of information but the master weavers of the cosmic web, using the threads of entanglement to bind the universe into a single, coherent whole. From the mind-bending idea that black holes could be connected by wormholes, we take one final, staggering leap into a concept that challenges our most basic perception of reality. If entangled connections can stitch the cosmos together, then perhaps the universe we experience is not the fundamental reality at all, but a magnificent projection. This is the essence of the holographic principle, a theory that proposes our three-dimensional universe with all its galaxies, stars, and planets is actually a hologram, a projection of information stored on a distant, two-dimensional surface. To grasp this, let's consider a puzzle that emerged from the study of black holes. When an object falls into a black hole, it seems to vanish, taking its information with it. But as we learned from the information paradox, quantum mechanics forbids the destruction of information. So where does it go? In the 1990s, physicists Gerard T. Hooft and Leonard Susskind proposed a radical solution. They suggested that all the information about what falls into a black hole isn't lost inside. Instead, it is somehow encoded on the black hole's event horizon, the two-dimensional boundary that marks the point of no return. Think of the event horizon like the surface of a pond. When you throw a stone into the pond, ripples spread across the two-dimensional surface. In a similar way, the information about an object falling into a black hole could be translated into a complex pattern of quantum bits or qubits etched onto the event horizon surface. The three-dimensional interior of the black hole with all its contents would then be a projection of that two-dimensional information. The black hole is a hologram. Now, the holographic principle takes this breathtaking idea and applies it to the entire universe. The cosmological horizon, the ultimate limit of what we can see, the farthest distance from which light has had time to reach us since the Big Bang, acts as the universe's equivalent of a giant event horizon. The principle suggests that everything within our observable universe, every particle, every force, and every galaxy, is a projection of information encoded on this vast, spherical, two-dimensional boundary at the edge of space and time. We are not just in the universe, we are a holographic image of data stored on its outermost shell. But what is the glue that makes this colossal hologram work? The answer, once again, is entanglement. For the holographic projection to be seamless and consistent, the information bits on the boundary cannot be independent. They must be deeply and intricately entangled with one another. It is this dense web of quantum connections on the two-dimensional surface that generates the illusion of a third dimension. The spatial depth we experience in the same way that the intricate interference of light waves creates the stunning depth of a holographic image on a credit card. Without entanglement weaving the information together, the projection would collapse into a meaningless, pixelated jumble. This brings our journey back to entangled galaxies in a profound new light. If two galaxies are entangled, their connection is not a mysterious force traveling between them in our three-dimensional space. Instead, according to the holographic principle, their entanglement is a fundamental reflection of how their information is encoded at the boundary. The quantum link between them exists because the qubits describing galaxy A and the qubits describing galaxy B are entangled on the cosmological horizon. Their apparent separation in 3D space is an illusion emerging from a deeper, interconnected reality. The cosmic web of galaxies we see is a direct manifestation of the entangled web of information on the universe's ultimate surface. This perspective suggests a truly unified cosmos. The universe is not a collection of things that sometimes become connected. At its most fundamental level, it is a single, unified system of information where every part is inextricably linked to the whole. The holographic principle, powered by quantum entanglement, paints a picture of a universe that is holistic and interdependent. The fate of a star in a galaxy a billion light-years away is woven into the same informational fabric as the device you're using to watch this video. It's a vision of reality where the ancient philosophical idea of as above, so below finds its ultimate expression in the laws of physics, revealing a cosmos that is far more interconnected, mysterious, and beautiful than we ever dared to dream. These mind-stretching ideas, from entangled dark matter to cosmic holograms, are no longer just speculative theories confined to chalkboards. Scientists are now designing ambitious experiments to search for the hard evidence of these quantum connections woven through the cosmos. The quest is to find a signature in the data that simply cannot be explained by the known forces of nature. Gravity alone cannot account for everything we see. The question is whether the subtle fingerprints of quantum entanglement are hiding in plain sight. One of the most promising avenues involves performing a cosmic version of the very same tests that confirmed entanglement in the laboratory. On Earth, physicists prove entanglement by measuring pairs of particles and showing that their properties are correlated in a way that exceeds any possible classical explanation. Astronomers are now adapting this logic to the grandest scales imaginable. They are searching for specific, anomalous correlations in the positions and velocities of pairs of galaxies that appear to be statistically linked beyond what gravity alone could orchestrate. Imagine studying two galaxies separated by such a vast distance that light has not had enough time since the beginning of the universe for any signal to have traveled between them. According to our standard understanding, these galaxies should be completely independent, their evolution governed solely by the local matter in their vicinity. Yet, if sophisticated statistical analysis of massive galaxy surveys reveals that these seemingly isolated galaxies are moving in subtly synchronized ways, that their distributions or velocities are more aligned than chance would allow, it would be a powerful hint of a deeper, non-local connection. It would be as if the galaxies were performing a coordinated dance, not because they can see each other, but because they are fundamental partners in a quantum sense. To detect these incredibly subtle signals, we need more than just powerful telescopes. We need a revolution in data collection. This is where next-generation observatories come into play, instruments with the sensitivity and precision to map the universe in unprecedented detail. The James Webb Space Telescope is already peering deeper into space and further back in time than ever before, capturing the faint light of the first galaxies. By providing exquisitely detailed information about the shapes, compositions, and motions of these ancient galactic structures, Webb gives us a sharper snapshot of the cosmic web in its youth. This data is crucial for testing models of how structure formed. If the distribution of these early galaxies shows patterns that suggest they emerged from an entangled quantum state in the early universe, it would provide compelling support for our hypothesis. But to truly test the dynamics of entanglement, we need to see the universe in motion. This is the goal of projects like the Square Kilometre Array, or SKA, a truly monumental endeavor in radio astronomy. When completed, the SKA will comprise thousands of radio antennas spread across South Africa and Australia, effectively creating a single telescope with a collecting area of over 1 square kilometre. This colossal instrument will be able to conduct a cosmic census on an unimaginable scale, mapping the positions and velocities of billions of galaxies across the entire sky. It will measure the faint radio emission from neutral hydrogen gas, allowing it to trace the large-scale flow of matter with phenomenal precision. The SKA will essentially create a three-dimensional movie of the universe's expansion and the movement of galaxies within the cosmic web. Within this immense river of data, scientists will be hunting for the faint statistical ripples that indicate galaxies are influencing each other through means other than gravity, the telltale whispers of quantum entanglement acting across millions of light years. Beyond mapping galaxies, other probes are looking at the fabric of spacetime itself. Precise measurements of the cosmic microwave background polarization, as we discussed, continue with ever more sensitive instruments. The detection of a specific type of polarized pattern, known as primordial B modes, could be the smoking gun for gravitational waves generated during the universe's inflationary birth. The character of these waves could reveal whether the inflationary field itself was quantum entangled, imprinting that connection onto the cosmos. Furthermore, studies of the cosmic distance ladder, the methods we use to measure how far away galaxies are, might reveal tiny anomalies in the expansion history of the universe. These anomalies could indicate that the strength of dark energy is not perfectly constant but varies in a way that reflects the underlying entangled structure of the quantum vacuum. Each of these experiments is like a different instrument in a grand orchestra, each tuning into a specific frequency of the cosmos. Individually, they provide valuable data, but collectively, they have the potential to harmonize into a symphony of discovery that completely reshapes our understanding of reality. The search for entangled galaxies is not a single, definitive experiment but a converging web of evidence where anomalies in galaxy motions, patterns in ancient light, and the very rate of cosmic expansion all point toward a single, interconnected truth. We are on the verge of moving from philosophical wonder to empirical science, using the universe itself as the ultimate laboratory to test the most profound idea of all, that we live in a quantum-entangled cosmos. This journey through the cosmic implications of quantum entanglement leads us to one of the most fundamental and perplexing aspects of our existence, the nature of time itself. Why does time seem to flow in one direction from a fixed past through a fleeting present into an uncertain future? We take this arrow of time for granted, as it's woven into the very fabric of our experience. Eggs scramble but never unscramble. Memories are of the past but not the future, and the universe expands but never contracts. This relentless forward march seems absolute, yet the fundamental laws of physics, from Newton to Einstein to quantum mechanics, are almost entirely time-symmetric. The equations work just as well if time runs forward or backward. So where does this overwhelming sense of direction come from? The answer may lie not in the laws themselves, but in the specific initial conditions of the universe, and quantum entanglement could be the hidden architect of time's arrow. To understand this, we need to look back to the very beginning. The early universe, moments after the Big Bang, was in a state of exceptionally low entropy, which is a measure of disorder or randomness. It was an incredibly hot, dense, but remarkably ordered and uniform state. Physicists believe this unique low-entropy starting point is the ultimate source of the arrow of time. As the universe expanded and evolved, it had nowhere to go but toward higher entropy, toward greater disorder and complexity. This increase in entropy is what drives all the processes we associate with time's flow. But this just pushes the question back a step. Why did the universe begin in such a special, low-entropy state? The intriguing possibility is that quantum entanglement played a decisive role in setting this initial condition. In the fiery first moments, every particle was in contact with every other particle, a single, unified quantum system. As the universe rapidly expanded during the period of inflation, these particles were pulled apart, but many remained entangled. This process of entanglement creation is profoundly linked to the increase of entropy. When two particles become entangled, the information about their individual states is lost, becoming shared information between them. This sharing of information, this growth of quantum connections, is a form of increasing entropy for the system as a whole. Therefore, the rapid and widespread establishment of quantum entanglement in the infant cosmos could have been the very mechanism that locked in the low-entropy boundary condition, launching the arrow of time on its irreversible flight. The universe started in a state of low entropy because its constituents were highly correlated through entanglement. As it expanded, those correlations were stretched and diluted, allowing entropy to rise and time to acquire its definitive direction. Now let's scale this idea up to the cosmic web. If galaxies are indeed connected by these primordial entanglement links, it fundamentally challenges our linear perception of time. We think of the past as gone and the future as not yet existing. But in a universe woven together by instantaneous quantum connections, this clean separation begins to blur. Consider two entangled galaxies. A measurement or a significant quantum event in one galaxy would be instantly correlated with its partner. From our classical, local perspective, we would see one event happen before the other if we're closer to one galaxy. But in the quantum reference frame of the entangled system, there is no before or after. The correlation is immediate and timeless. The past of one galaxy and the future of its entangled partner are not independent timelines. They are two aspects of a single, unified reality. This suggests a block universe view where the past, present, and future all exist simultaneously in a static four-dimensional space-time block. Our conscious experience of now is just a slice through this block. Quantum entanglement adds a stunning layer to this picture. The entangled correlations threading the cosmos are not laid down in time. They are what define the structure of the block itself. The connections between galaxies are not lines drawn through history. They are the stitches that hold the entire tapestry of spacetime together. In this view, the Big Bang isn't a moment lost in the distant past. It is a feature of the universe that remains dynamically connected to the present state of every entangled galaxy through these non-local links. The universe's birth and its ultimate fate are not separate events but are quantum correlated in points of a single, coherent whole. What does this mean for our understanding of reality? It implies that the flow of time we experience may be an emergent property, a consequence of our limited, localized perspective within a vastly interconnected quantum system. We are like fish sensing a current in a river, unaware that the entire ocean is interconnected. The arrow of time may be the direction in which quantum information becomes increasingly scrambled and distributed across the cosmic web via entanglement. As the universe evolves, the network of entanglement grows more complex, and it is this growing complexity that we perceive as the passage of time. The future is uncertain not because it hasn't been written, but because we, as localized observers, only have access to a tiny fraction of the entangled information that defines the whole. The cosmic dance of entangled galaxies is not happening in time. It is a timeless, correlated existence, and our journey from past to future is our conscious travel through its interconnected layers. Now, let's bring these cosmic connections down to a human scale and envision a future transformed by this knowledge. We've seen how entanglement might weave the universe together, but what if we could learn to weave it into our own technology? The most immediate and revolutionary application lies in the realm of communication. Today, our interplanetary conversations are painfully slow. A simple message from a rover on Mars can take up to 20 minutes to reach Earth and another 20 for a response. This light-speed delay isn't just an inconvenience. It's a dangerous barrier to real-time control of machinery, remote surgery for astronauts, or even a coherent conversation between planetary colonies. But if the cosmos is already threaded with quantum connections, we might not need to fight this delay. We could bypass it entirely. Imagine a future where we don't just send probes to other planets, but we also send quantum transceivers, devices designed to create and maintain a bank of entangled particles. The principle is similar to the laboratory experiments we do on Earth, but executed on an astronomical scale. A spacecraft destined for a new world would carry a source of entangled particle pairs. As it travels, it would carefully preserve one particle from each pair, while systematically projecting its partner back towards Earth or to a network of relay stations. Upon arrival at, say, a budding colony on Mars, the spacecraft would have a unique collection of particles that are intrinsically linked to partners millions of miles away. This shared quantum resource becomes the foundation for an instantaneous communication channel. The magic of quantum communication is its fundamental security. In a classical system, you can intercept and copy a message without the sender or receiver knowing. But with entangled particles, any attempt to eavesdrop on the quantum signal inevitably disturbs it. This disturbance is immediately detectable by the legitimate users. This means that a message sent via this quantum link isn't just fast, it's inherently unhackable. Financial transactions between worlds, sensitive diplomatic communications, and even personal family messages could be transmitted with absolute privacy, secured by the laws of physics themselves. This quantum internet wouldn't be built with cables and radio towers, but with a delicate web of light and matter, connecting humanity across the solar system into a single, secure network. The implications for exploration are staggering. A rover on the icy plains of Europa wouldn't be a slow, semi-autonomous robot waiting minutes for instructions from Earth. It would be a direct extension of a human pilot's will. An operator on a space station orbiting Jupiter could control the rover in real time, feeling the feedback through haptic gloves as if they were touching the alien ice themselves. Scientists on Earth could conduct live, interactive experiments on distant moons. This instantaneous link would transform space exploration from a series of pre-programmed commands into a truly interactive experience, dramatically accelerating the pace of discovery and reducing the risks for human pioneers. Looking even further ahead, this technology could be the key to navigating the interstellar void. Future generation ships traveling for centuries to reach another star system would face the agonizing prospect of becoming completely isolated from humanity. The light speed delay would stretch from minutes to years, effectively severing their connection to home. But if such a vessel could establish and maintain an entangled link, it would carry a thread of instantaneous contact back to Earth. The ship's inhabitants would never be truly alone. They could receive updates on technological breakthroughs, cultural shifts, and even personal news from a homeworld they left generations ago. This perpetual connection would change the very psychology of interstellar travel, turning a lonely exile into a continuous conversation across the light years, binding the human family together even as it spreads across the galaxy. The quantum threads that may bind the galaxies could one day bind our own civilization, turning the entire cosmos into a shared neighborhood. Building on the idea of instantaneous communication, our ability to harness cosmic entanglement could evolve into something far more profound, the capacity to literally feel the fabric of the universe. This next leap involves developing technologies that don't just use entanglement for signaling, but employ it as a supreme sensory organ for the cosmos. The key lies in creating ultra-precise quantum gravity sensors. On Earth, we already have prototype devices called atom interferometers that use the quantum wave nature of atoms to measure tiny variations in gravity. They can detect underground cavities, mineral deposits, or even the subtle gravitational pull of a small mass brought near the device. Now, envision scaling this principle up to an astronomical level, transforming an entire spacecraft or a network of orbital observatories into a single, colossal quantum gravity sensor. The principle would rely on maintaining a vast cloud of entangled atoms within the sensor. Because these atoms are quantum linked, they would act as a single, coherent system, incredibly sensitive to the most minute distortions in spacetime, the ripples of gravity. A traditional telescope sees light. This sensor would see gravity itself. It could map the invisible architecture of the cosmic web in real time, tracing the subtle gravitational gradients of dark matter filaments that are otherwise completely hidden from view. Instead of inferring the web's structure from the positions of galaxies, we would perceive it directly, watching as the gravitational tides of these vast cosmic rivers ebb and flow. This would be like switching from a world of flat photographs to a world of immersive, three-dimensional topographical maps, revealing the true gravitational landscape of the universe. With such an intimate map of the cosmic web in hand, humanity would graduate from being mere observers of the cosmos to potential shapers of it. This leads to the staggering concept of galactic engineering. If we can map the dark matter filaments with quantum precision, the next logical question is whether we could learn to influence them. Dark matter's gravitational pull is the primary force sculpting galaxies and governing the motion of stars within them. While the idea of manipulating something as exotic and pervasive as dark matter sounds like pure fantasy, the potential lever might be the very quantum connection we've been exploring. If dark matter particles are entangled, then influencing a local cluster of them through some advanced technology could, in theory, create a ripple effect that propagates instantaneously along the entire filament due to their non-local linkage. The applications of such a capability are as vast as the cosmos itself. Consider a star system facing a long-term threat, such as a slowly decaying planetary orbit that will eventually make a world uninhabitable. Rather than attempting the mind-boggling task of moving a planet with brute force, a galactic engineer might use a quantum gravity manipulator to apply a subtle, sustained nudge to the local dark matter halo. By carefully adjusting the gravitational potential well that the star system resides in, they could gently steer the planet's orbit back into a stable, life-friendly configuration. It would be a form of celestial feng shui, rearranging the invisible gravitational furniture to create a more harmonious environment for life. Looking even further, this knowledge could open up new pathways for interstellar travel that circumvent the limitations of light speed. We already entertain the idea of wormholes as shortcuts through spacetime. If the ER equals EPR conjecture holds true, and entangled black holes are connected by such structures, then understanding galactic-scale entanglement could be the first step toward finding or even stabilizing these natural cosmic tunnels. A civilization that can precisely map the entangled connections between supermassive black holes might be able to identify gateways pairs of black holes that form the most stable and navigable wormholes. The ultimate interstellar highway system would not be built by us but discovered, a pre-existing network woven into the fabric of the universe, waiting for a sufficiently advanced species to learn its rules and chart its courses. Perhaps the most profound energy source waiting to be tapped is the quantum vacuum itself. We've discussed how the seething energy of virtual particles might be the driver of dark energy. A civilization that truly comprehends large-scale entanglement might learn to harness this power not by extracting energy from nothing, but by orchestrating it. Imagine creating a device that can temporarily correlate a vast region of the quantum vacuum, synchronizing the random fluctuations of virtual particles to produce a coherent directional force. This wouldn't be a violation of energy conservation. It would be a matter of playing the probabilities of the quantum field on a grand scale, like a conductor guiding an orchestra of random notes into a powerful, unified chord. Such a vacuum engine could propel starships without the need for propellant, drawing on the underlying energy of spacetime itself. The ability to sense and then influence the cosmic web through entanglement marks the transition from a species that lives on a planet to one that can truly live with the galaxy, engaging with the universe on its most fundamental, interconnected level. This journey into the quantum cosmos now brings us to the most intimate frontier of all, the nature of our own minds. We've explored how entanglement might connect galaxies and shape the vacuum of space, but what if this cosmic web also touches the very essence of awareness? This leads us to the quantum consciousness hypothesis, a speculative but fascinating idea that proposes the weird rules of the quantum world are not just for particles, but might be fundamental to the phenomenon of consciousness itself. The central puzzle here is the so-called hard problem of consciousness. How does the intricate electrical and chemical activity of a brain, a collection of atoms and molecules, give rise to subjective experience? How do we get the rich inner world of thoughts, feelings, and sensations from mere biological machinery? Classical physics, which views the brain as a complex computer, struggles to explain this leap from objective process to subjective reality. Some scientists and philosophers suggest that quantum mechanics, with its inherent weirdness, might offer a missing piece. The brain is a warm, wet, and seemingly chaotic environment, which for a long time was thought to be far too hostile for delicate quantum effects like coherence and entanglement to survive. But growing evidence suggests that certain biological structures might be fine-tuned to protect quantum processes. Consider the humble photon in photosynthesis. In plants, light energy is captured and transported to a reaction center with near-perfect efficiency. For years, this process baffled scientists because the energy seemed to explore all possible pathways through the plant's cellular structure simultaneously before settling on the most optimal route. It turns out this is a quantum effect called superposition, where the energy exists in multiple states at once, guided by entanglement. This happens efficiently even at warm temperatures, protected within the precise structure of protein molecules. If nature can harness quantum mechanics for energy transfer in a sunlit leaf, could it have evolved similar mechanisms for information processing inside our skulls? One prominent theory focuses on structures within neurons called microtubules. These are tiny protein filaments that form the skeleton of our brain cells. The physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that these microtubules could be shielded enough from their environment to sustain quantum vibrations. In their orchestrated objective reduction model, these quantum processes within microtubules could collapse into a definite state in a way that gives rise to moments of conscious experience. While this theory remains highly controversial and is not accepted by the mainstream neuroscience community, it highlights a crucial point. We should not dismiss the possibility of quantum biology simply because the brain is a complex system. Now, let's scale this idea up to a truly cosmic level. If our individual consciousness has even a partial quantum basis, and if the universe is permeated by a web of large-scale entanglement, then a profound possibility emerges. Our minds might not be isolated islands of awareness. Instead, they could be subtly interfacing with this cosmic network. Think of your brain not as a closed-circuit computer, but as a quantum receiver, tuned to a faint background hum of universal connection. This doesn't mean you can hear the thoughts of aliens or receive messages from distant stars. The influence would be far more fundamental, perhaps shaping the very substrate of thought and intuition. Those moments of sudden insight, the feeling of profound connection to nature, or the sense of awe when gazing at the starry sky, experiences that have inspired art and science for millennia, could be more than just emotional responses. They might be glimpses of a deeper resonance, a subtle synchronization between the quantum processes in our neural circuitry and the entangled fabric of the cosmos. This perspective leads to an even more staggering proposal, that consciousness might not be solely a product of the brain, but a fundamental property of the universe itself. This idea, known as panpsychism, suggests that consciousness is as basic as mass or charge, present in some minute form in all matter. In this view, a single electron possesses an infinitesimal degree of proto-consciousness. What we experience as human consciousness is not something generated from nothing by our brains, but rather a complex, organized aggregation of these fundamental conscious properties, orchestrated by our neural architecture. Now combine panpsychism with galactic entanglement. If every particle has a rudimentary form of awareness, and if particles across the universe are quantum entangled, then the cosmos itself could possess a form of cosmic consciousness. The vast network of entangled galaxies wouldn't just be a physical structure, it would be a thinking, feeling entity on a scale beyond our comprehension. Our individual minds would then be localized knots of intensified awareness within this greater cosmic mind, much like individual neurons are specialized cells within our brain that contribute to our overall consciousness. This hypothesis, while deeply speculative, offers a radical re-enchantment of the universe. It suggests that the cosmos is not a cold, mechanical void, but a living, conscious whole. The laws of physics we discover are not just arbitrary rules, but perhaps the evolving thought processes of this cosmic entity. The emergence of life and intelligence on planets like Earth would not be a random accident in a dead universe, but a natural flowering of the universe's inherent potential for self-awareness. We are not just living in the universe, we are the universe becoming aware of itself through us. Our scientific quest to understand quantum entanglement and the cosmic web is, in this profound sense, the universe beginning to comprehend its own deepest nature. It blurs the line between the observer and the observed, suggesting that in the act of looking up at the stars and seeking to understand their connection, we are participating in a grand cosmic conversation with ourselves. As we stand on the precipice of these staggering possibilities, we are inevitably drawn into a deeper conversation, one that moves beyond the mechanics of the universe to question its very soul. The discovery of a deeply entangled cosmos forces us to confront profound philosophical questions that humanity has grappled with for millennia. If the universe is fundamentally interconnected, a single, unified system rather than a collection of isolated parts, does that suggest it has an inherent meaning or purpose? For centuries, scientific materialism has presented a universe that is largely mechanical and accidental, where life and consciousness are fortunate flukes in a vast, indifferent void. But the existence of a cosmic quantum web challenges this detached perspective. It paints a picture of a universe that is holistic, where every part, from a grain of sand to a swirling galaxy, is a participant in a grand, coherent whole. This doesn't necessarily prove the existence of a traditional deity, but it strongly implies a universe built on relationship and connection as a primary principle. Such a cosmos appears less like a random accident and more like a system that values integration and complexity, a universe that seems almost designed to produce conscious beings capable of perceiving its intricate beauty and underlying unity. This shifts the philosophical ground from a universe of separation to one of profound relationship, suggesting that our search for meaning might be aligned with the fundamental architecture of reality itself. This new cosmic story also resurrects an ancient debate between determinism and free will with startling new energy. If every particle is linked in a vast, timeless block universe where the past and future are quantum correlated, where does that leave our sense of agency? Are our choices truly our own, or are they simply the inevitable unfolding of a cosmic script written at the Big Bang? The entangled cosmos offers a fascinating middle path. Our lives are not predetermined in a rigid, clockwork sense. Instead, we are active participants within a responsive, interconnected network. Every thought, every decision we make might send subtle ripples through the quantum field, influencing the whole in ways we cannot yet perceive. Our free will could be an emergent property of our complex, localized position within the cosmic web. We are not powerless cogs in a machine. We are dynamic nodes, making real choices that contribute to the ongoing evolution of the universe. Our consciousness becomes the means by which the cosmos reflects upon and chooses its own future, blending destiny with genuine agency in a dance of co-creation. With this awe-inspiring vision of connection, however, comes an immense ethical responsibility. The potential to develop technologies that manipulate cosmic entanglement forces us to consider the consequences of wielding power on a universal scale. This is not like splitting the atom, it is like learning to pluck the strings of space-time itself. The primary ethical imperative is the precautionary principle on a galactic level. Before we even attempt to nudge a dark matter filament or stabilize a wormhole, we must achieve a near-perfect understanding of the cosmic ecosystem. A miscalculation wouldn't just lead to a local disaster, it could have unforeseen repercussions across light years, potentially disrupting the gravitational balance of star systems or altering the very expansion rate of the universe. The development of such technologies cannot be the project of a single corporation or nation. It must be a collective endeavor for all of humanity, governed by transparent international frameworks and a deep reverence for the cosmic order we are seeking to influence. This leads to the critical question of cosmic equity. If a handful of advanced civilizations gain the ability to manipulate the large-scale structure of the universe, what obligations do they have toward emerging intelligences or even lifeless planets with the potential for future life? Reshaping a galaxy for your own species' benefit could inadvertently sterilize nascent biospheres or alter the evolutionary pathways of countless other worlds. This introduces a cosmic version of the Prime Directive, a foundational ethic of non-interference born from the recognition that the universe is a shared, precious, and delicate inheritance. The power to reweave the cosmic web must be paired with the wisdom to know when to let it be, to preserve the natural, billion-year processes that gave rise to us and may give rise to others. Ultimately, the greatest philosophical shift ushered in by the entangled cosmos might be a renewal of cosmic empathy. For generations, we have felt small and alone in the darkness. But if the quantum connections are real, then we are not insignificant observers on a tiny rock. We are integral threads in the living tapestry of the universe. The star stuff we are made of is in constant, silent conversation with the hearts of distant galaxies. This knowledge invites us to shed our anthropocentric view and adopt a cosmocentric perspective. Our well-being is not separate from the well-being of the whole. Protecting our planet, fostering peace, and pursuing knowledge are not just human concerns. They are contributions to the health and evolution of a conscious, connected cosmos. The ethical charge for our species, should we choose to accept it, is to grow into our role as responsible stewards of this magnificent, entangled reality, using our newfound powers not for domination, but for nurturing the profound connections that bind us all. For generations, storytellers have grappled with the human desire to conquer distance, dreaming up technologies that would shrink the universe to a manageable scale. Perhaps the most famous of these is the Ansible, a term coined by the brilliant author Ursula K. Le Guin for a device that allows for instantaneous communication across any distance. This concept was later adopted and expanded by writers like Orson Scott Card in Ender's Game, where it becomes essential for commanding fleets in interstellar war. The Ansible embodies a core science fiction trope, the complete and utter bypassing of light-speed lag. It's a clean, reliable, almost magical technology that works because the plot requires it to, connecting characters as easily as a telephone call. Similarly, Frank Herbert's Dune presents us with the Spacing Guild and their dependence on the spice melange. This substance doesn't create entanglement, but it allows guild navigators to safely pilot faster than light ships by granting them a form of prescience, enabling them to see a safe path through folded space. In both cases, the technology is presented as a tool, a solved engineering problem that society has seamlessly integrated, much like we have with the internet today. The reality of quantum entanglement, however, is both more restrictive and far stranger than any science fiction trope. The most critical distinction is what entanglement cannot do. It cannot transmit information faster than light in any way that violates causality. This is the fundamental rule that science fiction often cheerfully ignores. Think back to our pair of entangled quantum dice. You roll your die on Earth and see a 3. You know instantly that the die on Mars also shows a 3, but here's the catch: you have no control over what number your die will show. The outcome is random. More importantly, your friend on Mars has no way of knowing that you've rolled your die until you send them a message by a classical channel like a radio signal, which is limited by the speed of light. They look at their die, see a 3, but without your radio message, they have no context. For all they know, they could have looked at their die a minute ago. Entanglement creates a correlation, but not a communication channel. It's like having two synchronized clocks. You can see what time it is where your friend is, but you can't use the clocks to send a message. This limitation points to the second major difference, the sheer fragility of the quantum state. Science fiction devices are robust. They work in starship engine rooms and survive battles. Real-world entanglement is incredibly delicate. Maintaining the coherence of entangled particles, keeping them in their linked, fuzzy quantum state, requires isolating them from any interaction with the external environment. A single stray photon bumping into a particle can cause decoherence, collapsing the quantum state and severing the spooky link. This is why the most advanced quantum experiments on Earth are conducted in ultra-high vacuum chambers, cooled to temperatures a fraction of a degree above absolute zero. The idea of having a handheld Ansible that works reliably in a pocket or on a bridge of a vibrating starship is, with our current understanding, a physical impossibility. The cosmic scale offers a more promising environment due to the natural vacuum of space, but harnessing it would involve monumental engineering feats far beyond simply flipping a switch. So, if entanglement can't be used for sending messages, where does the exciting, realistic possibility lie? The answer is in quantum encryption and quantum sensing, which are arguably even more revolutionary than a simple Ansible. The very property that prevents faster-than-light communication, the fact that any attempt to observe or measure an entangled system disturbs it, makes it the perfect foundation for unhackable communication. If you use a stream of entangled photons to create a secret key, any eavesdropper trying to listen in will inevitably alter the quantum states, alerting the legitimate users immediately. This is not science fiction. It's happening now with terrestrial quantum networks. Scaling this to a solar system-wide quantum internet is a credible goal for the next century. It wouldn't allow for faster-than-light chats, but it would provide absolute security for the light-speed communications we already rely on, making the future Internet of Planets fundamentally secure from the ground up. Furthermore, while we can't send messages through entanglement, the correlation itself is a powerful tool for sensing the universe with unparalleled precision. This is where a comparison to the Spice of Dune becomes intriguing. The Guild navigators use the spice to perceive folded space. We could use networks of entangled sensors to perceive the universe in a new way. By placing entangled atomic clocks on different planets or spacecraft, we could create a galaxy-spanning interferometer. Because the clocks are linked, they could detect infinitesimally tiny ripples in spacetime gravitational waves, with a sensitivity far beyond anything possible today. This wouldn't be about moving faster than light, but about seeing more clearly. We could map the gravitational landscape of the solar system, detect small asteroids by their minute gravitational pull, or listen to the echoes of the Big Bang with incredible detail. In this sense, entanglement becomes less like a telephone and more like a new type of eye, allowing us to observe the cosmos through the lens of quantum-connected gravity. So, while we may never have a dramatic Ansible call, we might one day have a silent, instantaneous, and universal alert system that tells us the precise state of our quantum-secured infrastructure, or a sensor web that lets us feel the heartbeat of the universe itself, a reality that is, in its own subtle way, more profound than the fiction. But how do we possibly sift through this avalanche of cosmic data to find the faint whispers of quantum connection? The answer lies not just in bigger telescopes, but in smarter ones. We are now enlisting a powerful new partner in this search: artificial intelligence. The datasets from observatories like the James Webb Space Telescope and the Future Square Kilometre Array are so colossal, so complex, that traditional methods of analysis are simply overwhelmed. It's like trying to find a single, specific grain of sand on every beach on Earth by hand. artificial intelligence and machine learning are becoming the indispensable tools that allow us to navigate this ocean of information, acting as expert guides to patterns and correlations that would be utterly invisible to the human eye. These AI systems are trained to look for the statistical ghosts of entanglement. Imagine you have a photograph of a vast forest. A human can see the individual trees, but could you spot if the leaves on two trees miles apart were subtly trembling in perfect synchrony, even when there was no wind to connect them? That's the kind of needle in a haystack problem we face. AI algorithms can be set loose on maps of millions of galaxies, meticulously comparing their positions, shapes, and velocities. They aren't biased by our classical expectations of how gravity should work alone. They can search for those tiny, anomalous correlations, those synchronized tremors between galaxies that should be causally disconnected, that might be the signature of a deeper quantum link. These aren't simple patterns, they are hyperdimensional relationships in a dataset of billions of points, a space where only AI can effectively operate. Beyond just analyzing observations, AI is revolutionizing our ability to simulate the universe itself. To understand if entanglement can work on a galactic scale, we need to model it. But simulating the quantum fields of an entire galaxy, let alone the cosmic web, is a computational task of almost unimaginable difficulty. The number of variables is astronomically large. Here, AI-driven simulations are breaking through previously insurmountable barriers. Scientists are now using a technique called neural network quantum state tomography. In essence, they train an artificial neural network to represent the incredibly complex wave function of a quantum system. This AI-based model can then simulate the behavior of that system over vast scales and long periods of time, far more efficiently than conventional supercomputers. It's like having a brilliant physicist who can intuitively grasp the behavior of a billion interacting particles at once, testing how quantum correlations might persist and influence the formation of cosmic structures over billions of years. This partnership between human curiosity and machine intelligence is crucial because it helps us overcome our own cognitive biases. We are naturally inclined to think in terms of local cause and effect. An AI has no such preconceptions. It can uncover correlations that seem nonsensical or spooky to us, simply because it follows the data without prejudice. It might identify a strange relationship between the polarization of light from quasars at opposite ends of the sky and the distribution of galaxy clusters, a connection that no human theorist would have thought to propose. In this way, AI isn't just a tool for confirmation, it's an engine for genuine discovery, generating new hypotheses about the quantum nature of the cosmos that we can then test with even more focused observations. This creates a powerful feedback loop. AI analyzes data to find anomalies, theorists develop models to explain them, and then new AI-driven simulations test those models against reality, accelerating our understanding at an unprecedented pace. The search for an entangled universe is a puzzle of cosmic proportions, and artificial intelligence is proving to be the key that allows us to see the bigger picture. The gentle chime that wakes Ilara is not a sound, but a feeling, a subtle shift in the quantum state of the atoms in her wristband. A silent, instantaneous signal from the network that the Titan colony's orbital day has officially begun. She opens her eyes not to an alarm clock, but to the soft, ambient glow of her bedroom, which is already adjusting its spectrum to mimic the sunlight now hitting the domes of Saturn's largest moon. Her first conscious act is to reach for the smooth, cool surface of her interface stone. It doesn't have a screen in the traditional sense. Instead, as her fingers make contact, her mind is gently flooded with the morning's updates. There are no laggy video messages. Her partner, Kale, who is on a geological survey near Titan's methane lakes, isn't speaking to her from the past. The entanglement link means their conversation exists in a shared present. She feels the texture of his thoughts, the data stream of his morning findings on subsurface ice formations arriving not as a delayed file, but as an immediate experience perfectly synchronized across 1 billion kilometers. It's less like reading a message and more like sharing a moment, a testament to a solar system that has finally learned to whisper to itself in real time. After a breakfast synthesized from molecules patterned on Earth soil templates, Elara steps out into the transit hub of her orbital habitat. The era of staring at blinking dots on a screen to plot a course is a distant memory. Her personal mobility pod is guided by a gravity wave navigator, a system that doesn't just map the obvious gravitational pulls of planets and stars. It taps into the faint, intricate ripples of the cosmic web itself. As she settles into the contoured seat, the holographic display doesn't show a simple line from point A to point B. Instead, it reveals the local spacetime as a dynamic topographical landscape. Dark matter filaments, those invisible rivers of gravity, glow with a soft amber light indicating optimal flow paths. Turbulent areas where micro-black holes or dense energy fields create gravitational eddies are highlighted in soothing blues, suggesting routes to avoid. The navigator isn't calculating a path through space so much as it's finding the path of least resistance within the fabric of spacetime, a ride on the cosmic currents. Her commute to the Biodome laboratory is not just efficient. It's a serene, perfectly orchestrated journey along the invisible architecture of the universe. Midday brings her scheduled wellness scan, a routine as common as checking the weather once was. She places her palm on a crystalline reader in her lab's wellness nook. This isn't a medical device that bombards her body with radiation or draws blood. It works by reading the quantum coherent state of the entangled particles naturally present in her own cellular water. The device compares this delicate quantum signature against a baseline that is itself dynamically calibrated to the cosmic background. The theory, now well established, is that human health is not just a biochemical state but a quantum harmonic one, subtly influenced by the resonant frequencies of the universe. The scan doesn't just look for pathogens or imbalances, it assesses her body's alignment with these deeper cosmic rhythms. Today, the feedback is a soft, reassuring pulse of green light and a simple data stream suggestion. Her quantum coherence shows a slight dip in neural synchrony, likely from the intense mental focus of her morning work. The system gently recommends a 15-minute session under the habitat's central arboretum dome, where the precise vibrational frequency of the genetically tailored ancient redwoods is known to help recalibrate neural quantum states. Her health is no longer managed in isolation but is understood as an integral part of a vast, interconnected system, where a walk among trees can literally tune a person to the music of the spheres. As her workday concludes, Elara's evening is shaped by this pervasive connectivity. She dines with friends who are physically present on the habitat, but the table's immersive projector also includes the lifelike avatars of colleagues from the Martian Science Archives and an artist from a floating city in the clouds of Venus. The conversation flows without a hint of delay, the entanglement links ensuring that a laugh or a thoughtful pause is shared simultaneously, making the distances between worlds feel as meaningless as the distance between chairs. Later, as she prepares for sleep, the habitat's environment subtly shifts again. The ambient light dims into frequencies that encourage the brain's transition into restful quantum states, synchronized with the quietest gravitational pulse of the local cosmic web. Lying in the darkness, Elara doesn't feel small or isolated. She feels embedded. The same quantum threads that allow her to speak instantly with Titan and travel via gravity's flow also bind the molecules of her body to the dance of distant galaxies. In this future, humanity hasn't conquered the cosmos. It has learned to listen to it, to live in harmony with its deepest, most spooky, and most beautiful connections. A day's routine is a silent conversation with the universe, and every action is a testament to a reality that is, and always has been, profoundly one. Now, let's take the ultimate leap and envision a form of travel that leaves rockets and warp drives behind, a concept that transforms the very idea of a journey. Instead of traversing the immense distances between stars, what if we could simply step through space, using the cosmic web's quantum connections as a network of natural doorways? This is the promise of interstellar travel via entanglement tunneling, a technology that wouldn't propel a ship but would reconfigure its relationship with spacetime itself. The principle hinges on taking a quantum effect observed in the lab and scaling it up to a cosmic magnitude. In the microscopic world, quantum tunneling is a well-known phenomenon where a particle, like an electron, can pass through an energy barrier that it classically shouldn't be able to overcome. It's not that the particle smashes through the wall. Rather, there's a finite probability that it will simply appear on the other side, as if a tiny tunnel momentarily opened through the obstacle. This isn't science fiction, it's a fundamental part of how transistors work and essential to nuclear fusion in the sun. Now, imagine if we could induce this effect not for a single electron but for an entire spacecraft. The challenge is astronomical, as the probability of such an event for a complex object is infinitesimally small. This is where large-scale entanglement provides the key. If 2 points in spacetime, say, a region near Earth and a region orbiting a star in the Orion Nebula, are quantum entangled, they are, in a sense, the same location in the fabric of reality. The immense empty void between them becomes the barrier to tunnel through. By manipulating the entangled states of these two regions, a technology of unimaginable sophistication could, in theory, amplify the tunneling probability to a near certainty, effectively causing the spacecraft to disappear from one point and reappear at its entangled partner instantaneously. The experience of such a journey would be utterly unlike any form of travel we can conceive. There would be no sense of acceleration, no roaring engines, and no years spent in cryogenic sleep. The process would begin with the activation of what we might call a quantum displacement drive. The ship would be positioned at a stable nodal point within the local cosmic web, a place where the entanglement links are strongest. Passengers would likely enter a protected quantum coherence field, a necessary step to ensure that every atom in their bodies and the ship tunnels in perfect synchrony. As the drive engages, the world outside the viewports wouldn't stream by as stars, it would simply dissolve. There would be no sensation of movement through space because, in a very real sense, the ship isn't moving. Instead, the coordinates of its location in the universe are being rewritten. The transition might be perceived as a momentary flicker, a brief discontinuity in consciousness, or perhaps a dazzling flash as the ship's quantum state is resolved at the destination. One moment you're looking at the familiar constellations of home, the next you're staring up at an alien sky with a foreign sun casting strange shadows across your hull. The vast interstellar distance hasn't been crossed, it has been rendered irrelevant, collapsed into a single quantum step. Of course, the technological hurdles to achieving this are beyond our current comprehension. The first and most daunting challenge is the creation and maintenance of a stable, macroscopic entanglement link between two distant points in space. We're not talking about linking two particles, but linking two vast regions of spacetime, each containing countless particles. This would require an energy source capable of manipulating the fabric of reality on a stellar scale, perhaps harnessing the power of entire stars or tapping directly into the quantum vacuum energy we discussed earlier. The second challenge is the sheer computational power needed to calculate and control the quantum state of an object as complex as a starship. Every atom, every molecule, every memory stored in a computer bank would need to be quantum teleported with perfect fidelity. Any error in the process could lead to catastrophic decoherence, where the ship and its passengers fail to reintegrate properly at the destination. Finally, there is the existential challenge of navigation. We would need an exquisitely detailed map of the cosmic web's entanglement architecture, identifying which stars are quantum twins and which pathways are stable enough for transit. A wrong calculation could see a ship tunneling into the heart of a star or being lost in the void between galactic filaments. This isn't a technology for the reckless. It is the endpoint of a civilization that has fully mastered the quantum laws of the cosmos. Yet, if achieved, it would unlock the galaxy not as a frontier to be painfully crossed, but as a network of interconnected rooms waiting for us to open the doors. But if entanglement truly weaves the cosmos into a unified whole, then perhaps the past is not a distant country lost to time, but a record that is still accessible, etched into the very quantum connections we've been exploring. This leads us to the extraordinary concept of quantum archaeology, a theoretical science that wouldn't dig through rock and sediment, but through the foundational layers of reality itself. The idea is that if the universe began as a single, intensely entangled quantum state, then the patterns of those initial connections should, in principle, still be imprinted on the cosmos today. An advanced civilization wouldn't need a time machine to witness the Big Bang. They might simply need a sensitive enough quantum sensor to read this cosmic ledger, to detect the faint but persistent echoes of the first moment. Think of the universe not as an expanding balloon, but as a block of pristine, clear ice. When the ice first freezes, any tiny vibration or impurity creates internal fractures and patterns that are frozen in place. As the ice melts or is carved, those internal flaws remain, telling the story of its formation. In our analogy, the quantum fluctuations of the infant universe are the initial vibrations, and the rapid expansion of inflation is the freezing process. The patterns of entanglement created in that first fraction of a second were then stretched across the entire cosmos, frozen into the large-scale structure. The cosmic microwave background is like the first light shining through that ice, revealing its initial surface imperfections. But quantum archaeology proposes that with even greater sensitivity, we could peer inside the ice, reading the deeper, three-dimensional network of fractures, the quantum entanglement that dictates how galaxies cluster and how dark matter is distributed. By meticulously mapping the precise quantum correlations between millions of galaxies, a future scientist could work backwards, using the rules of quantum mechanics to reconstruct the state from which they all evolved. It would be like hearing a symphony and, from the complex harmonies of the instruments, deducing the composer's original score. The key to this monumental task lies in the fundamental property of quantum mechanics called unitarity, which, as we discussed, states that information is never lost. The specific quantum information of every particle at the moment of the Big Bang, its spin, its energy, its relationship to every other particle, must still be encoded in the universe in some form. The challenge is that this information is horribly scrambled and distributed across the cosmos. It's the ultimate detective story where the clues are scattered across billions of light years. However, if a civilization could build a galaxy-spanning network of quantum sensors, perhaps using the entangled atomic clocks we mentioned earlier, they could create an interferometer of unimaginable scale. This device wouldn't just listen for gravitational waves. It would be sensitive enough to detect the residual quantum vibrations between entangled galaxy clusters. These vibrations would be incredibly faint, a whisper of a whisper, but they would carry a unique signature, a timestamp pointing directly back to the era of their creation. By correlating these signals across the entire observable universe, a powerful artificial intelligence could begin to unscramble the data. It would look for patterns of correlation that defy classical explanation, the same way a cryptographer looks for non-random patterns in a coded message. These patterns would be the fossilized imprint of the universe's primordial quantum state. The ultimate goal would be to run the simulation of cosmic evolution backwards, not with approximate models, but with the actual quantum data extracted from the present. This wouldn't be a guess about the past, it would be a direct playback. Imagine focusing this quantum telescope on a region of empty space. Instead of seeing darkness, the sensor data is fed into a visualizer and slowly an image resolves, not of the present but of that exact location 13 billion years ago, showing the hot, dense plasma of the early universe with galaxies beginning to condense like droplets in a mist. You wouldn't be looking at a simulation, you would be reconstructing a historical record from data that has been there all along, waiting to be read. The implications of such a capability are as profound as they are humbling. Quantum archaeology would transform cosmology from a forensic science based on inference into a direct historical discipline. We could finally witness the first moments of inflation, settling debates about how the universe began. We could observe the formation of the very first stars and galaxies directly, rather than piecing it together from their ancient redshifted light. But it also raises profound questions. Could we use this technique to observe specific events in Earth's history? In theory, if every particle on Earth is part of the universal quantum network, its history is also encoded. However, the signal from a single planet would be impossibly drowned out by the cosmic background noise. Reading a specific event would be like trying to hear a single conversation from one person in a crowded sports stadium by only listening to the vibrations in the stadium's foundation. It's likely that quantum archaeology would be limited to the very largest scales, the grand events that shaped the cosmos itself. Yet, even with that limitation, the ability to watch the universe's greatest movie, the story of everything from the first spark to the formation of our own galactic home, would represent the ultimate achievement of a scientific civilization, a testament to the idea that the past is never truly gone, but merely waiting for us to learn how to see it. Yet the most immediate impact would likely be felt in the very fabric of our global economy, potentially creating a divide more profound than any we have ever known. Imagine a world where the first entities to master the principles of cosmic entanglement, be they corporations or nations, gain the ability to build a quantum-secured internet. This wouldn't just be a faster internet, it would be an inherently unhackable network, rendering all current digital security obsolete overnight. Financial transactions, military communications, and sensitive data would flow with absolute privacy, protected by the unbreakable laws of physics. Those outside this new quantum infrastructure would be left in a digitally vulnerable dark age, their systems transparent and easily compromised. The power imbalance wouldn't stop at communication. The ability to use entangled sensors for ultra-precise gravity mapping could lead to a new era of resource discovery, locating mineral deposits and energy sources deep within planets or asteroids with pinpoint accuracy. This could create an unprecedented concentration of wealth and strategic advantage, birthing a new class of quantum-capable powers while leaving others struggling to catch up. The very stars and the empty space between them, once a shared human inheritance, could become a new frontier for economic and political domination. This technological stratification could spill over into our daily lives in deeply personal ways, potentially giving rise to a new form of social inequality. Access to healthcare, for instance, could be revolutionized by quantum biometric interfaces that monitor our well-being at a subatomic level, as we glimpsed in Ilara's daily routine. But what if such advanced care is only available to a privileged few? We might see a society split between those whose health is constantly optimized through synchronization with cosmic rhythms and those reliant on outdated, less effective biological medicine. This divide could extend to education, with neural interfaces allowing for the instantaneous download of complex knowledge streams, creating a cognitive gap between enhanced and unenhanced individuals. The fundamental question would become, in a universe that proves our intrinsic connection, do we have a responsibility to ensure that the fruits of that connection are shared by all humanity, or will it become just another commodity, amplifying the divisions we already struggle with on Earth? Amidst these practical upheavals, a deeper, more philosophical revolution would be unfolding. For centuries, many spiritual and indigenous traditions have spoken of a universal interconnectedness, a concept often dismissed by materialistic science as poetic metaphor. The confirmation of galactic entanglement would validate this ancient wisdom with the full authority of empirical data. We would have to confront the possibility that the cosmos is not a cold, mechanical void but a unified, conscious entity, as some panpsychist philosophies suggest. This could spark a profound spiritual awakening, a collective cosmic empathy where harming our planet or each other is seen not just as a local tragedy but as a disruption to the entire web of existence. Environmentalism would gain a new, powerful imperative. Protecting Earth's biosphere would be understood as maintaining the health of a single, precious node in a galactic network. Our sense of identity would expand from being citizens of a nation to being stewards of a cosmic garden, fostering a global ethic of care and responsibility. This new cosmic philosophy would inevitably challenge the foundations of our existing religions and belief systems. Some might incorporate the science of entanglement into their theology, viewing the quantum web as the physical manifestation of a divine presence or plan. Others might see it as a threat, a reduction of sacred mystery to mere physics. A new form of cosmic spirituality could emerge, one that finds awe not in supernatural miracles, but in the breathtaking, spooky elegance of the universe's own operating system. The drive to explore space would be transformed. It would no longer be just about survival or conquest, but about communion, about reaching out to touch the other nodes of the network, to learn from them, and to understand our role within the whole. The greatest discovery would not be a new planet, but a new purpose, to grow into a species worthy of its place in a connected cosmos, using our knowledge not for domination, but to nurture the profound and beautiful connections that bind us all. Of course, such a mind-bending vision of a quantum-connected cosmos doesn't arrive without its fair share of raised eyebrows and rigorous counter-arguments. To present this idea as anything but a highly speculative frontier would be a disservice to the scientific method itself. The path to rewriting physics is paved with bold hypotheses, but it is the relentless skepticism of the scientific community that ensures only the most robust ideas survive. So, let's step into the shoes of the skeptics and examine the monumental challenges that stand between this beautiful theory and its acceptance as established fact. The most immediate and formidable obstacle is the same phenomenon that makes quantum computers so difficult to build: decoherence. In the pristine cold of deep space, decoherence is reduced, but is it reduced enough? Skeptical physicists argue that even in the near-perfect vacuum between galaxies, there are still potent sources of disruption. The universe is bathed in a sea of low-energy photons from the cosmic microwave background, and it's crisscrossed by cosmic rays, high-energy particles racing at near-light speed. A single interaction with one of these particles could, in theory, sever a delicate quantum link. Maintaining entanglement between two particles in a lab on Earth is a Herculean task requiring incredible isolation. Proposing that such a connection could persist between entire galaxies across billions of years is a leap that many find simply too great to make. The question isn't just whether entanglement can exist over such distances, but whether it can survive the relentless, chaotic background noise of the universe for a timescale longer than the age of the cosmos itself. It's like suggesting a single, perfectly tuned violin string could continue to vibrate in harmony with another, even while both are suspended in a hurricane. Beyond the problem of mere survival, there's the deeper issue of mechanism. How exactly would galaxies become entangled in the first place? The standard model of cosmology, which describes the universe's evolution from the Big Bang using well-tested physics, is spectacularly successful. It explains the cosmic microwave background, the abundance of light elements, and the large-scale structure of the cosmos with remarkable precision, all without invoking any large-scale quantum weirdness. Skeptics point out that the correlations we see in the cosmic web, The filaments and clusters of galaxies are elegantly explained by gravitational instability acting on dark matter over billions of years. Adding quantum entanglement to the mix is, in their view, an unnecessary complication. It's a case of Occam's razor. If a simpler explanation already fits the data beautifully, why introduce a more complex and unproven mechanism? They argue that the apparent spookiness in the data, like the synchronized patterns in the cosmic microwave background, might not be a sign of quantum connection but rather a statistical fluke, an artifact of how we measure the sky, or a clue pointing to a new type of classical physics we have yet to discover. Prominent voices in theoretical physics urge caution. They highlight that leaping from the proven, microscopic realm of quantum mechanics to the astronomical scale of galaxies is a dangerous extrapolation. The rules that govern atoms are not necessarily the same rules that govern clusters of galaxies. While the ER=EPR conjecture is a fascinating and active area of research, it remains just that, a conjecture. There is no direct observational evidence for wormholes connecting black holes, let alone galaxies. Until such evidence is found, these ideas remain in the realm of elegant mathematical possibility rather than empirical reality. This healthy skepticism is the engine of scientific progress. It forces proponents of cosmic entanglement to sharpen their theories, to make more precise, testable predictions that can be verified or falsified by the next generation of telescopes and experiments. The drama of this scientific debate is not a weakness. It is the very process through which our understanding of the universe is forged, tested, and ultimately transformed. So how do we move from these compelling theoretical hints and statistical anomalies to undeniable proof? The answer lies in a type of experiment so audacious it makes the Large Hadron Collider look like a tabletop demonstration. We need to perform a definitive test, one that can distinguish between a universe where correlations are just a lucky coincidence and one where they are fundamentally, spookily connected. On Earth, this test already exists. It's called a Bell test, and it proved Einstein wrong. Now we must scale it up to a cosmic level. We need to build a galactic Bell test. The core principle is beautifully simple, yet its execution would be the most complex undertaking in the history of science. A Bell test, at its heart, is a way to check if two particles are truly entangled or if their correlation can be explained by some hidden local variable. It works by measuring specific properties of each particle, like the polarization of a photon along different angles chosen at random. If the particles are truly quantum entangled, their measured properties will be correlated in a very specific, mathematically defined way that simply cannot be replicated by any theory where information is confined to travel at or below the speed of light. This is what it means to violate a Bell inequality. It's the smoking gun for quantum weirdness. For a galactic scale test, we wouldn't be looking at two photons in a lab. We would be looking at two entire regions of the cosmos, treating them as if they were the two particles in the experiment. Imagine launching two incredibly advanced space probes, not to a single planet, but on epic, millennia-long journeys to opposite sides of our galaxy, or even to two nearby, seemingly unconnected galaxies within the same galactic cluster. These wouldn't be ordinary spacecraft. They would be mobile quantum observatories, their sole purpose to serve as distant measuring devices in the ultimate physics experiment. Each probe would carry a suite of detectors designed to measure a specific cosmic signal that could act as our quantum property. One promising candidate is the polarization of light from ancient quasars. Quasars are the intensely bright cores of distant galaxies powered by supermassive black holes. Their light, after traveling for billions of years, carries a specific polarization signature. The proposal is to identify pairs of quasars that, according to our standard cosmological models, should never have been in causal contact since the beginning of the universe. Their past light cones do not overlap. The experiment would unfold over centuries. Once the probes reached their designated positions millions of light-years apart, they would begin their work. They would simultaneously and randomly choose an angle at which to measure the polarization of the light from their assigned quasar. This randomness is crucial. It ensures that no hidden signal could have pre-arranged the outcome. The probes would record their measurements with exquisite precision, and then, here's the catch, they would need to send that data back to a central location like Earth using conventional light-speed communication. This is the ultimate patience-testing part of the experiment. We would have to wait perhaps for millions of years for both sets of data to arrive. Then comes the moment of truth. Scientists, or more likely, their AI descendants, would finally compare the two datasets. They would analyze the correlation between the polarization measurements from the two impossibly distant quasars. If the correlation is weak or follows a pattern that can be explained by classical physics, then Bell's inequality would hold and the dream of cosmic entanglement would fade. But if the measurements from the two ends of the universe are correlated in that very specific, mathematically spooky way that violates Bell's inequality, it would be a discovery that reshapes human thought forever. It would be direct, irrefutable evidence that the two quasars, and by extension the regions of space they illuminate, are parts of a single quantum system. It would confirm that non-locality is not a quirk of the tiny, but a fundamental feature of the cosmos on its very largest scales. The challenges are, of course, beyond our current imagination. The technological hurdles involve building quantum detectors stable enough to function flawlessly after million-year journeys through interstellar space, creating random number generators of impeccable quality, and developing power sources that last for eons. There's also the profound challenge of ensuring the experiment remains intact. A single micrometeorite impact or a software glitch after 10,000 years could invalidate the entire mission. Yet, the very act of designing and launching such an experiment would represent a monumental leap for our civilization, a declaration that our curiosity extends beyond our own lifespan, beyond even the lifespan of our species. We would be planting a flag for knowledge in the far future, undertaking a project whose final results might only be seen by a humanity that has evolved into something we can scarcely envision. The galactic Bell test is more than an experiment. It is a message in a bottle tossed into the cosmic ocean, a testament to our enduring need to understand the true and perhaps beautifully entangled nature of our home. So where does this breathtaking journey leave us? We have followed the threads of evidence from the spooky link between photons in a lab to the synchronized dance of galaxies across the void. From the mysterious cohesion of dark matter halos to the possibility that dark energy itself is the breath of an entangled quantum vacuum. We have even considered that our own consciousness might be a localized expression of a cosmic mind. Each piece of the puzzle, when viewed separately, is a fascinating anomaly. But when we step back and look at the complete picture, a single, staggering question emerges from the cosmic fog. Could the entire universe, in all its magnificent complexity, actually be a single, gigantic quantum object? This is the profound idea of a monistic universe. Monism, from the Greek word monos meaning alone or single, is the philosophical position that all of reality is fundamentally one substance, one essence. In this view, the countless stars, planets, and people we see are not truly separate entities. They are instead like whirlpools in a vast river, temporary dynamic patterns that arise from a single flowing whole. The separateness you and I feel from the screen in front of us, from the air we breathe, even from the distant Andromeda galaxy, would be the ultimate illusion. Quantum mechanics, with its insistence on non-locality and entanglement, provides the first rigorous scientific framework for this ancient intuition. If every part of the cosmos is instantaneously connected to every other part, then the universe isn't just a collection of things that interact. It is one single, unified system. We are not just pieces of the universe, we are the universe experiencing itself from a billion different points of view. The implications of this shift are so radical they can be difficult to fully grasp. It redefines our understanding of space and time. In a monistic, entangled cosmos, space isn't an empty container that holds separate objects. It is more like the connective tissue of this single quantum entity. The vast distances between stars are not gulfs of emptiness separating islands of matter. They are an integral part of the whole, the stretched-out fibers of the cosmic fabric that allow for its intricate structure. Similarly, time may not be a linear progression of cause and effect, but rather the process by which this unified system evolves and expresses its interconnected nature. The Big Bang wouldn't be the beginning of many things, but the moment this single quantum object began to unfold and differentiate, like a seed germinating into a complex plant. This perspective also forces us to reconsider the nature of individuality and free will. If we are all fundamentally part of one whole, where does one person end and another begin? Our sense of being a distinct, autonomous self remains a powerful and real experience, but in the monistic view, it might be akin to a single cell in a body insisting on its complete independence from the organism. Our choices and actions would not be the products of an isolated will, but rather localized expressions of the universe's own unfolding intelligence. This doesn't eliminate free will, instead it recontextualizes it. Our freedom becomes the freedom of the whole cosmos to express itself creatively through us. We are the universe making choices, feeling love, and asking questions about its own origin. Embracing this view could have a transformative effect on our species. For centuries, a worldview of separation has underpinned conflict, exploitation, and environmental disregard. If we see others and the natural world as fundamentally separate from ourselves, it becomes easier to justify harm. But if the monistic vision is correct, then harming another person or polluting a river is quite literally a form of self-harm. It is the left hand trying to cut off the right. This understanding could foster a deep, innate sense of cosmic empathy and responsibility. Our drive to explore space would no longer be about conquering external territory, but about getting to know other aspects of our own vast self. The ultimate goal of science would shift from controlling nature to understanding our place within this magnificent, unified whole. The universe may not be a cold, mechanical clockwork, but a single, living, thinking process, and we are its awakening eyes and conscious mind. And so we find ourselves at the end of an extraordinary voyage, a journey that began with the baffling behavior of particles in a lab and has stretched our imagination to the very edges of the cosmos. We started by peering into the spooky heart of quantum mechanics, where two particles can share a fate across any distance, a concept so strange it troubled even Einstein. From that tiny, paradoxical seed, we followed the trail of clues as it expanded to an astronomical scale, exploring the breathtaking possibility that this same quantum connection might be the invisible glue holding the universe itself together. We've seen how the vast, empty voids between galaxies could be the perfect sanctuary for preserving these delicate links, how the cosmic web might be threaded with quantum filaments, and how even the mysteries of dark matter and dark energy could be manifestations of a deeply entangled reality. This is more than just a new theory. It is a fundamental shift in perspective, inviting us to see the cosmos not as a collection of isolated islands, but as a single, breathing, interconnected whole. If this vision of a quantum-woven universe is correct, the implications for our future are nothing short of revolutionary. The technologies that could emerge from this understanding would seem like magic to us today. We could move beyond the frustrating lag of light-speed communication, building a quantum-secured internet that connects humanity across the solar system with absolute privacy and instant correlation. Imagine piloting a rover on a distant moon in real time, or receiving health updates that synchronize your body's rhythms with the cosmic background. We might develop sensors that allow us to see the gravitational landscape of the universe, navigating space-time not as an empty void, but as a dynamic topography of currents and flows. Further ahead lies the staggering potential for galactic engineering, where we could learn to gently nudge the invisible dark matter scaffolding of star systems to ensure their stability, or even discover natural wormholes bridges through space-time that turn the galaxy into a network of interconnected rooms. This isn't just about building faster ships, it's about learning to listen to the universe's deepest language and perhaps one day learning to speak it. But beyond the promise of future technology, this paradigm shift offers us something even more precious, a new story about our place in the cosmos. For centuries, the scientific narrative has often emphasized our smallness and isolation, painting a picture of a cold, mechanical universe where we are accidental spectators. The entangled cosmos tells a different story. It suggests that we are not merely living in the universe, but that we are an intimate expression of it. The same quantum threads that connect distant galaxies are woven into the fabric of our own beings. When we gaze up at the starry night sky, we are not separate observers looking out at a foreign realm. We are the universe looking back at itself, becoming conscious of its own astonishing beauty and complexity. This understanding fosters a profound sense of cosmic empathy, where caring for our planet and each other is recognized as tending to a single, magnificent system of which we are an inseparable part. The journey to uncover these mysteries is far from over. It is just beginning. The questions we've explored today sit at the bleeding edge of science, where brilliant minds are debating, experimenting, and peering into the data for those crucial telltale signs. The path forward will require immense patience, powerful new tools like the Square Kilometre Array, and the guiding intelligence of artificial intelligence to help us see patterns hidden in the darkness. It is a quest that will challenge our deepest assumptions about space, time, and reality itself. So, the next time you find yourself under a clear night sky, look up. Let your eyes trace the faint band of the Milky Way and consider the possibility that you are not looking at a void, but at a web, a living, thinking network of connections beyond our current comprehension. Stay curious, support the pursuit of knowledge, and never stop wondering about the beautiful, spooky, and entangled mysteries that lie just beyond the edge of our understanding, waiting for